Concluding the section 3.1 notes, we now turn to an application of quadratic functions to problems involving finding a minimum or a maximum value. This is based on the result, the following result that you see at the top of the page 4 of the notes. The vertex represents the point at which a quadratic function attains its maximum or minimum value, since it's either the highest or the lowest point on the graph. And specifically, it's the y-coordinate of the vertex that represents the maximum or the minimum value. This is summarized with the following result. Given the quadratic function f of x equals ax squared plus bx plus c, which in standard form would be written ax minus h squared plus k, where the vertex would have the form hk. First of all, if the value of a is negative, the parabola opens down. Therefore, the vertex is the highest point on the parabola, and the y-coordinate of the vertex, which is k, would be the maximum value of the function. If a is positive, the parabola opens up. Therefore, the vertex would be the lowest point on the graph, and from that it would follow that the y-coordinate of the vertex k would be the minimum value of the function. So we want to look at the sign of a to determine whether we get a maximum or a minimum, and then determining the vertex, the y-coordinate of the vertex will represent the actual minimum or maximum value. Let's look now at example 5. The total revenue R earned per day in dollars from a certain business is given by R of P equals negative 12P squared plus 150P, where P is the price charged in dollars per unit sold. Revenue is just amount of money earned from sales of some product. Here the revenue is a function of the price at which each particular item is sold. The question is, what price will yield the maximum daily revenue, and what is that maximum revenue? Well, what we notice is that our revenue function is a quadratic function. It's quadratic in the variable p rather than in the variable x. So the p is really acting like the x in this particular situation. So what we need to determine is the vertex of the parabola that is given by this particular function. And because the parabola opens down, since a is negative here, a is equal to negative 12, and b is equal to 150, it's R of p equals ap squared plus bp plus c. So a is negative 12, b is 150, c is 0 in this case. Since a is negative, we're going to obtain a maximum based on the result that we just stated above. That's because the parabola represented from this particular function opens down. So the vertex is the highest point. So the maximum occurs at the highest point of this parabola. So what are the coordinates of the vertex? Well, the coordinate, what we normally call the x-coordinate, but here we'll call it p, the p sub v. The p-coordinate of the vertex by the vertex formula is minus b over 2 times a. But b is 150, so that would be negative 150 over 2 times negative 12. That is negative 150 divided by negative 24. And that works out to be 6.25. So what we would normally call the x-coordinate of the vertex, here we call it the p-coordinate, is 6.25. Now again, A is negative, so the value of the y-coordinate of the vertex would be the maximum value of the function. So that would be determined by substituting 6.25 into the revenue function. So that would mean we would compute negative 12 times 6.25 squared plus 150 times 6.25. And using a calculator, I won't show any more details than that. Using a calculator, the value we would obtain is 468.75. So this would represent our maximum revenue, where the price per unit would be $6.25. The maximum revenue would be $468.75. Now I want you to notice on the parabola, what we have simply found are the coordinates of the vertex, the highest point on the parabola. And if you look, you can see that looks about right. 6.25 for P, this would be your values of P, and your values of R are given by the vertical scale. And you can see that the value of P does appear to be about 6.25, and the actual revenue itself is slightly less than $500, a little bit less than $500, and that would correspond to the value we found, $468.75. So to conclude, we can say the maximum revenue is $468.75 when the price per unit is $6.25. For prices, for prices other than $6.25, the revenue is less than that amount. By the way, I just noticed when I wrote price per unit, I didn't have the T in the right spot. I corrected that there just so you're aware in case you couldn't read what I was writing. As our final example, let's look at a problem where we have to create the function for ourselves. Find two numbers whose difference is 10 and whose product is a minimum. So this is another min-max type problem. And what I've provided here is a table that shows different pairs of numbers whose difference is 10. For example, 12 and 2, 8 and negative 2, because 8 minus negative 2 is 10, and so on. And then I'm also showing their products, which vary. And you can notice that when you have 5 and negative 5, you get negative 25, which is, at least among the pairs of numbers shown in the table, the smallest, the minimum product of those numbers. So it would appear from the table perhaps 5 and negative 5 would be the two numbers we're looking for. But we want to try to do this, get the result beyond any doubt. And for that purpose, we can set up a quadratic function to represent the situation. So we could begin this by saying let S and T be the numbers we're looking for. Now we are given that the difference between S and T is 10. So what we want to do is we want to minimize the product of s and t. I'll call that p. So that'd be s times t. Now, what we have currently is a function of two variables. I'd like to write that as a function of one variable. So if s minus t equals 10, it follows that s is t plus 10. That is, if we add t to both sides in the equation s minus t equals 10, then we get s equals t plus 10. So what we could do then is replace s in the product s times t with t plus 10. That gives the product as a function of t only. P of t is t plus 10 times t, or t squared plus 10t. And what we obtain is a I apologize, I had a little trouble with my computer there again. I've had quite a bit of trouble today with the computer. It's amateur hour, what can I say? So we obtain a quadratic function p of t equals t squared plus 10t with, it's actually ax squared plus bx plus c, except we have t instead of x, and we have a equal to 1, b equal to 10. Now, a is positive, which means that at the vertex of this quadratic function, the function value would attain a minimum. And the function value here would correspond to the product. So by finding the t-coordinate of the vertex, we can identify the value of t that would minimize the product. So the t-coordinate of the vertex would be, by the vertex formula, minus b over 2 times a. b is 10, a is 1. We obtain negative 10 over 2, which is negative 5. So if t is negative 5, then the product should be minimized. Okay, what about the value of s? Well, s is t plus 10. So that would be negative 5 plus 10 is positive 5. So indeed, when s is 5 and t is negative 5, their difference is 10, and their product, which happens to be negative 25, is a minimum. So the numbers would be 5, starting over, the numbers would be 5 and negative 5. And by the way, I have just a moment here. If we evaluate p at t equals negative 5, p of negative 5 would be negative 5 squared plus 10 times negative 5. That is 25 minus 50, and we obtain negative 25 for the actual minimum product of these two functions, which again corresponds to what we saw in our table. So with my computer freaking out and being out of time anyway, that wraps up section 3.1. Sorry for the technical problems.